Okay guys, here we are picking up where we left off yesterday. Right at the end of the hour yesterday we were talking about, from geometry, a tangent line and a secant line. And you recall a tangent line just skated right along the edge of the circle and intersected at one point. A secant line crossed through the circle and intersected that circle at 2 points. There are things called secant lines in curves or in functions. So let's draw a quick picture of this so that we can get an idea of what a secant line is. We're just going to make a quick sketch of this function right over here, y equals x squared plus 1. Alright, so I'm just going to start plotting some points here. Since I'm going just from x is -1 to x is 3, let's just plug in some points to get a graph. So -1 squared is 1, plus 1, 2. So -1, 2. Plug in a 0, that's 1. Plug in a 1, 1 squared is 1 plus 1, 2. Plug in a 2, 2 squared is 4 plus 1, 5. Three squared is 9 plus 1, 10. So 3, oh boy, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You're going to have to estimate here, and yes, I know it goes over our previous problem, but that's okay. Alright, so here's this graph right there. Now, you know this graph continues on, so I'm just going to kind of dot it out here. This secant line goes from this point right here at -1 comma whatever that y value was, which we know it was 2. So from -1, 2, up to 3 comma, there's the y value at 3, which we figured out was 10. So here's the secant line. There's the secant line for a function. A secant line just connects any 2 points on a curve. Secant line just connects any 2 points on a curve. So there's that secant line. And I'm asking you to write an equation of that secant line. Don't make this hard. This is just writing the equation of a line that goes through those 2 points. Let's use point slope form of a line. Y minus y coordinate equals slope times x minus an x coordinate. And you can pick either point that you want, either the -1 comma 2 or the 3, 10, and we just plug that in. X coordinate 3, y coordinate 10, slope. Slope, that's your average rate of change, is finding the slope of that line between here. So let's see, 10 minus 2 is 8 over 3 minus the -1, 4. 8 over 4 is 2. Average rate of change is slope of that secant line. Now I opted to put in that point 3, 10. It would be perfectly acceptable for you to say, use this point right here, which would be y minus 2 is 2 times x plus 1. They look very different, but if you were to put that in slope-intercept form, solve for each one for y, you would get exactly the same thing. All right, let's come down here and take a look at a word problem. An open box with a square base is required to have a volume of 10 cubic feet. Express the amount A of material used to make such a box as a function of the length x of a side of the square base. How much material is required for a base of 1 foot by 1 foot? How much material is required for a base of 2 feet by 2 feet? Use a graphing utility to graph A, that's the area, as a function of x. For what value of x is A the smallest? All right, here we go. An open box with a square base is required to have this volume of 10 cubic feet. So we are going to draw a box. So start off by drawing a rectangle here. And we're going to draw another rectangle slightly off, up and to the right. But draw those two sides solid. Draw the left side of that second rectangle and the bottom of that second rectangle as dotted. Then solid here, solid here, solid, dotted. Isn't that pretty? There's our rectangular box with a square base. So let's mark that. There's the base down here on the bottom. That's a square. So we've got this so far. We want to express the amount A of material used to make such a box as a function of the length x of a side of the square base. So that's x, that's x, that's x, and that's x. And we are looking for amount of material, so area as a function of length, area as a function of x. So we're looking for an equation to be area equals blah, blah, blah with x's in it. Area as a function of x. So when we look at this thing, if we want to find this area, looking at this box, clearly we have the bottom and the area of that bottom piece, that's a square. So the area here is x squared. And only one of them, because it's open top, open box. So the box, the top up here is open, so we don't include that top piece. But we do have these four sides. Well, the area of one side is x on the bottom times this height. We don't know that. Let me call that some height h. And we'll have four of those, front, back, left, and right. And each one has an area of x times h. That side box here, or that side here. So we have four x h's. Right now, though, we have area as a function of x and h. We need to get rid of that h. There's another piece of information in this problem that we haven't used yet. Right up here, see where it says the volume is 10 cubic feet? For a rectangular box, we know that volume is length times width times height. And volume's 10. Length and width are the same thing, so that's x squared times that height. Could we solve for h here? H is 10 divided by x squared. Now take that h, which is 10 over x squared, and plug it up here for that h, so that our area equation now is x squared plus 4x times 10 over x squared. Simplify. A equals x squared plus, that's 40 over x. Okay, that's part A. Area as a function of x. Done. All right. Part B. How much material is required for a base of 1 foot by 1 foot? Part B. 1 foot by 1 foot, so we're going to plug right in there. Area is 1 squared plus 40 divided by 1. The material that's needed then is 40 feet squared of material. It's area, so it's feet squared. How about required for a base of 2 feet by 2 feet? Well, that area is 2 squared plus 40 divided by 2. And again, I'm just plugging into this area function down here. The area is x squared plus 40 divided by whatever that x is. And this is 4 plus 20, so 24 feet squared. The last bit, let's use a graphing utility to graph this function. Grab your calculators. I mean it. Get your calculator. All right, let me clear that out. Let's type this in. X squared plus 40 divided by x, zoom 6. Ew. All right, first off, when you're looking at your graph, you got to kind of think about what's typed in where. Area, that's like y. That's y1. So the y value is area. The x value is the length of a side. Well, right up here, we knew that if the side length is 1, then the area is 40. And if side length is 2, then the area is 24. We're on a standard viewing window. No wonder we don't see anything over here. This stuff doesn't matter over here because that's negative x values. And side lengths can't be negative. So I'm going to go in, I'm going to change my window. I don't need to see all these negatives down here, but personally I like to see my axes whenever I can. So I'm going to change that to be a -1. On the minimum, I'm going to leave that maximum at 10. Y's, maybe I'm going to leave that at -10. I know I need to see at least 40 up here. Let's go a little bit bigger. How about 60? Graph. There's that function. And that's the important piece that we want, is positive x values, positive y values. X side length must be positive, y area must be positive. So we want this section in the first quadrant, which is what we have. Okay, now go through and do that minimum value for A. Yes, you do this too. Minimum 3, left bound. Now, you've been scrolling. Let me show you this. Rather than scrolling for a left and right bound, if you know the scale down here, you can just type it. And I know that I was counting by ones down here, so clearly my minimum is right around 2, 2.5, or 3. So I'm going to put a minimum value there of 1. Right bound, again, rather than scrolling, I can just know clearly that's way up here around 4 is a right bound, so I just put that in and hit enter. Guess is around 2, and there we go. So that minimum value for x is 2.714, 3 decimal places minimum please, and those are feet. Okay? Let's look at this next problem. On July 1st, 2004, the Cassini probe became the first spacecraft to orbit the planet Saturn. Although Saturn is about 764 times the size of Earth, it has a very similar gravitational force. The height s of an object thrown upward from Saturn's surface with an initial velocity of 100 feet per second is given as a function of time t in seconds by this: s of t, negative 17.28 t squared plus 100 t. Use a graphing utility to graph this. Determine the time at which height is a maximum. What is the maximum height? And then relate that to Earth. So first part, let's go here and let's graph. Now again, I do want to point this out to you that there's your equation, but when we type that in, this s is height, and that's going to be where your y1 value is. This t is time, and that's going to be in your calculator as x. So when we do this, negative 17.28 x squared plus 100 x. Again, I've said this a number of times, I can't reiterate it enough. Don't push graph right away, because then you're on your last window that you had, which you had adjusted. Go zoom 6, standard viewing window, and then make adjustments if necessary. All right, this graphed pretty quickly up here. Clearly see some piece going up and some piece coming back down. So we're going to have to see more up here, more y values. Let's go ahead and set those upper y values. Oh, let's try 100 and see if that's big enough. Not quite big enough up here. Now again, x is representing time. Do we need anything about negative time? No. So I'm going to get rid of that, those negative x values, and we're going to increase our y's. So window, let's drop this to like, oh, negative 1's good. 10's fine for the upper x value. And y's, let's send that to 150, 200. What do you think? I'm going to try 200. Oh, beautiful. Nice, pretty graph. All right, so here we go. Use a graphing utility to graph that function. Done. Determine the time at which height is a maximum. So let's go ahead and just run maximum on this. And again, if you want to use your typing here instead of scrolling, we knew we were counting off by ones. So my maximum, clearly 1, 2, I'm going to go 2. And if you choose the wrong one and that line is in the wrong spot, then you can just start all over again and change it. Right bound, let's go 4. Guess. And there's our maximum. Determine the time at which height is a maximum. So which of these coordinates is time? Yes, it's the x coordinate, so that's 2.893, and those are seconds. What is the maximum height? Well, the height is the y value here, so that maximum height is 144.675, and height is in feet. Okay. All right, just a word. Some of you all are having a heart attack because I left that as a 5, and I didn't round that 5 up to a 6. And I left this as 893 instead of rounding that 3 up to a 4. And when you do that, when you just chop off the decimal and you don't actually round, it's called truncating. Truncate. And you may truncate or round. Truncate is to chop off the decimals. Without rounding. And if I don't say one way or the other, then you may do either one. You may round or truncate. It makes no difference to me one way or the other. All right, let's look at this next one. The same object thrown from the surface of the Earth would have a height given by this one. Determine the maximum height of the object on Earth and compare this to your result from part C. So now come back to y equals and go down here to y2. Now let's put in this equation, negative 16x squared plus 100x. Now if you're on a color calculator, you can see the different colors. If you're on a black and white calculator, arrow over all the way to the left over to here, and then you won't have these choices, but you could just hit enter through and change the thickness of that line. Oops. And I'm just hitting the right arrow. You're on the non-color calculator, you just keep hitting enter until you change the thickness of that line to the desired. And then you can tell the difference between them. So now we're going to graph. Very, very similar. When you have two curves on here and you want to find the maximum, now mine's the red one, so I'm going to find the, no, that looks, yeah, I'll fix it later. I want to find the maximum on that red one, so we're going to go second calc, maximum. Now, up here at the top, it tells you what function you're on. If you want to be on the other function, on my red one, then I'm going to hit the up or down arrow to change. And now we can see that I'm on that second function, and it tells me up here that that's the function I want. Left bound of that function, you can scroll through this time if you want. Enter. Scroll through to the other side, enter, and a guess. There's that maximum value for Earth. What is the maximum height on Earth? 156.25 feet. Okay. Earth, if you compare these, on Earth, that object will go higher. It takes a little longer to get to that maximum height. It took 3.125 seconds. A little bit longer to get to that maximum height, and it does go farther up on Earth. Okay? Last problem. Right here. Oh boy, looks kind of scary to begin with. The Internal Revenue Service Restructuring and Reformed Act, or RRA, was signed into law by President Bill Clinton in 1998. A major objective of this RRA was to promote electronic filing of tax returns. The data in the table show the percentage of individual tax returns filed electronically for the years 1998 to 2006 when this textbook was published. Since the percentage P of returns filed electronically depends on the filing year, Y, and each input corresponds to exactly one output, the percentage of returns filed is a function of the filing year. So P of Y represents the percentage of returns filed electronically for the filing year Y. Again, a lot of background information in here. Lots of background information. It's telling you where this data is coming from. It's also explaining to you that it's a function. You're given a year, and we know how many percent or what percentage of tax returns were filed electronically. There's only one percentage for each year, so this is a function. All right, so, and we are just going to look here, find the average rate of change for the percentage of e-filed returns from 1998 to 2000. And remember, average rate of change is slope. Change in y over change in x. Change in y over change in x. So for part A, average rate of change from 1998 to 2000, 1998 to 2000. So 27.6 minus 20.7 divided by 2000 minus 1998. Let's see if we can do some of this in your head. 27.6 minus 20.7. 27.6 minus 20.7, come on, come on, come on, come on. 6.9. 2000 minus 1998, 2. All right, 6.9 divided by 2, 3.45. Percent per year. Percentage, that's the units here, per year here. So this is 3.45% per year. Okay. Part B. Find the average rate of change from 2001 to 2003. So it's still the same 2-year period, but this time from 2001 to 2003. So we're going to go with 40.2 minus 30.7 over 2003 minus 2001. Hey, I'll help you out with the denominator. It's 2. 40.2 minus 30.7, 9.5. 9.5 divided by 2, 4.75% per year. And the last one, part C, oh, not the last one, I'm sorry, C, still a 2-year period. This one's 2006 to 2004. 57.1 minus 46.5, that's 10.6 divided by 2, 5.3% per year. All right, now part D. What's happening to the average rate of time change as time passes? So still a 2-year time period, but here from 98 to 2000, 2001 to 2003, 2004 to 2006. So what's happening to that average rate of change over a 2-year period as we go on in time? Yeah, that's increasing. That average rate of change is increasing. What do you think is happening now? Significantly more than 57.1%. I don't remember what percentage it is, but it's a whole lot more than 57% of the people filing e-returns. Just think how more prevalent computers are in the last 10 years, since 2006 to 2016. Were iPhones around in 2006? No. Laptops in 2006? No. So significantly more computers available to people, so clearly, absolutely, we're going to have more filing electronically. Okay, there you go. This last page, left blank on purpose. We are done with this section. Thank you very much. If there's any time left today, please use it to work on test corrections or the homework for sections 2.1, 2.2, or 2.3. And tomorrow, Friday, is a work day in class. Enjoy the time. Have a nice weekend. See you Monday.